Artificial intelligence is no longer the future. It is the present we live in and the future we are preparing for. This FDP aims to equip us with the knowledge, insights, and competencies to navigate this exciting technological frontier. With immense joy and heartfelt gratitude, I welcome each one of you to the inaugural ceremony of the Atal Faculty Development Program on Frontiers of Artificial Intelligence, Theories, Frameworks, and Cutting Edge Applications. We are truly delighted to commence the 6-day learning journey and extend my sincere appreciation to all participants who have joined us from various institutions across the country. Your presence reflects your commitment to continuous learning and academic excellence. To begin with, it is my privilege to extend a warm and respectful welcome to our principal, Dr. C.B. Joseph. His unwavering support, visionary leadership, and encouragement form the foundation on which programs like this take shape. Sir, we are truly grateful for your constant guidance and motivation in all our academic endeavors. Also delighted to welcome Reverend Father Bichu Kundakat, Bursar and Course Coordinator. Further, your encouragement, timely guidance, and inspiring presence play a vital role in bringing this FTP to life. We deeply appreciate your efforts in nurturing academic initiatives and providing continuous support to our department. It is indeed an honor to extend a very special and heartfelt welcome to our esteemed chief guest and inaugurator, Dr. Sunil Titi, Director of ICFOS. Sir, we are truly privileged to have you with us this evening. Your remarkable contributions in the field of free and open source software, engineering education, and applied machine learning have inspired countless learners and educators. We look forward to hearing your insights and are grateful for your presence amidst your busy schedule. I also extend my warm welcome to all the distinguished faculty participants joining us for this FTP. The field of artificial intelligence is expanding at an extraordinary pace, reshaping industries, education, and society. Over the next 6 days, we hope to create a platform that encourages meaningful discussions, collaborative learning, and exposure to cutting-edge advancements in AI. Your active participation will make this program intellectually vibrant and enriching. On behalf of St. George's College, Aruvithura, and Department of Computer Applications, I welcome each and every one of you to this academic celebration of ideas, innovation, and knowledge sharing. We look forward to a fruitful and inspiring week ahead. Thank you, and once again, a warm welcome to all. Leadership is about inspiring progress and guidance towards excellence. We are privileged to be led by such a visionary leader, Dr. C.B. Joseph Sir, Principal of St. George's College, Aruvithura. May I humbly invite Dr. C.B. Joseph to deliver the presidential address.
Most respected course coordinator and Bazaar of the college, Reverend Father Biju Gunnekat, Honorable Chief Guest, Dr. Sunil Titi, Head of the Department of Computer Applications, Dr. Justin Joy, FDP Coordinator, Dr. Saumya George, other faculty members, and my dear participants. A very good evening to all of you. It gives me great pleasure to address you all in this online faculty development program on the frontiers of artificial intelligence. At a time when artificial intelligence is rapidly reshaping every aspect of education, research, industry, and society, initiatives like this become truly significant. As teachers, it's our responsibility not only to understand the emerging technologies, but also equip our students with the skills and perspectives needed for the future life. I am delighted to note that we have participants joining us from various institutions across India. I take this opportunity to extend a warm welcome to all of you. Your presence reflects the growing interest in artificial intelligence and the shared commitment to academic excellence. I am sure this diversity will enrich our discussions and promote meaningful collaboration. This faculty development program offers an excellent opportunity to explore cutting-edge developments in artificial intelligence, from machine learning and data science to advanced applications in influencing our everyday lives. I believe the sessions will broaden your perspectives and inspire new directions in teaching and research. I extend my sincere appreciation to the Department of Computer Applications of our college for their hard work and to the resource persons for generously sharing their expertise. I encourage all participants to engage actively and make the most of this learning experience. Wishing you all a productive and insightful program. Thank you.
Thank you, sir, for your thoughtful and motivating words. A program's success rests on the encouragement and guidance of supportive leaders. It is our pleasure to invite Father Bichu Kundaka, Bursar and Course Coordinator to offer his felicitation. Over to you, Father.
The president of this meeting, Professor Dr. C.B. Joseph, sir, Dr. Saumya George, Dr. Sunil T.T., Dr. Justin Joy, and my dear participants in this wonderful FDP program. First of all, I would like to, I wish you all a very fruitful session. As I understand, this is going to take place in the coming 6 days. Of course, AI has become one of the inevitable part of our daily life. From school students to experts working in different fields are using the wonderful opportunity of this AI and its support in many ways. I fear that sometimes it's going to overcome our human limitations and other problems because it can suggest any solution for any problem. That is one of the important attractions of this AI phenomena today. But very recently, our present Pope Leo the 14th suggested, rather he said, as he was addressing the young people at the National Catholic Youth Conference that was held in November 2025, he said, AI will not judge between what is truly right and wrong. It won't stand in authentic wonder before the beauty of God's creation. It gives us a lot to think about it. And of course, I am sure that AI has got an implication in different parts of our life, different areas of our life, but still there are areas where the human dignity is to be upheld and where our human thinking is very much valuable. Of course, I am sure that in these coming 6 days, all of you are going to contribute very much to this wonderful topic, and all of us are going to gain so much from this faculty development program. I wish all success to all of you, and especially would like to congratulate who are organizing this program, especially the faculty of St. George's College, Aruvithura. Wish you all very best and God's blessings. Thank you.
Thank you, Father. A program of this stature truly becomes complete with the presence of visionary leaders. We are deeply honored to have with us Dr. Sunil T.T., Director of ICFOS, a pioneer institution in free and open source technologies. With great respect, I invite Dr. Sunil T.T. to deliver the inaugural address. Over to you, sir.
Okay. So, am I audible? Right?
Yes, sir.
Okay.
Yes, you are.
So, good evening, everyone, and respected Principal, Bursar, the coordinator, and Justin, all other participants. Thank you for inviting me over here. It's a pleasure to be associated with a prestigious institute like St. George College, Aruvithura. And I think there are a lot of other excellent talks coming up in the line. I was just browsing through the brochure that the college gave me. So in this era of artificial intelligence, I think an FDP like this is most important to make people understand how things are standing out, how people will respond to the various challenges like ethics, or maybe of things like biases, etc. Also, local applications, etc., are very important, and it's a very good initiative to educate students, faculty, and even others into this one. Maybe it's a pleasure for me to inaugurate this 5-day faculty development program here. Maybe immediately I will switch over to my talk here rather than boring you with the conventional blah blah blah. Maybe I think shall I begin my lecture immediately, or do you have anything else coming up?
We can start, sir.
Okay, good. So let me share my slides first. Just a second. See how many participants? 167. No, so almost all of them are faculty, or I think are all for faculty, right? Yeah. So
Mostly faculty.
yeah.
PG students are also there.
Yeah, PG students are also there. My slides are visible, right?
Yes,
Yes.
sir.
Okay.
Sir, before starting your session, may I give a brief introduction of you?
No,
Sir,
it's
with your
fine. That's why I
permission?
was asking. Okay,
Yeah,
sure.
okay.
Please.
Okay, sir. So now we move on to the first technical session of the FTP, led by our esteemed resource person, Dr. Sunil TT, Director of ICFOS. Sir will be taking the session on Introduction to AI, Modern Tools and Techniques, setting the foundation for the days ahead. Dr. Sunil TT is a distinguished academic and technology leader with extensive expertise in free and open source software, engineering, education, and technology management. He holds a PhD in electrical engineering from IIT Bombay and has served in diverse roles, including IT consultant at the Kerala Legislative Assembly, professor, and principal of the College of Engineering at Atal, where he played a key role in establishing the institution. He has contributed significantly to the Kerala Technological University through roles in curriculum development, e-governance, and the Academic Council, and currently serves on the Board of Studies for Electronics. Dr. Sunil is also a member of the CUSAT Senate, the Kerala State Curriculum Committee, the Kerala Startup Mission Executive Committee, and is an adjunct faculty member at the Kerala Digital University. His research focuses on applied machine learning, including gesture recognition, large language models, and vision transformers, supported by numerous publications, funded projects, and PhD supervision. He presently heads ICFOS, Government of Kerala, and remains an active advocate of force technologies while also pursuing interest in amateur radio, law, privacy, and cyber legislation. Over to you, sir.
Okay, thank you for that nice intro. Now let me come to. I think this is for 1.5 hours. I hope. I think the session is scheduled like that, right?
Yes, sir.
Yes, sir.
Yeah. So it's a pretty long time for an online audience of say around 200 people are there, 150 people are there. So to keep the attention. Anyway, let me try out. So I'll be slow, but I will try to cover up all the research dimensions and the areas that currently we are moving through. So in order to understand the idea, so this is one of the first slides that I will show people whenever I start a lecture on AI. So is it possible to identify which is the? I hope that is visible, right? Is it visible? My video is visible
Yes,
over
sir.
there?
Yes,
Ah,
sir.
yeah.
Visible.
So,
Yes, sir.
can you identify which one is the original and which one is the duplicate or fake? So it's these days it is very difficult. Earlier, when we were trying to build AI systems, it was very difficult. It was easy to identify the fakes. Now I think everywhere, everything has in every aspect of human life, people are introducing AI-generated things, images, videos, speech, etc. So my agenda for today's lecture will be somewhat like this. So I will try to define the ideas behind human intelligence. How do we learn something when as a kid? And then I will move on to how computers learn. And then probably I will speak out what is a machine learning model. Then maybe the new sensation, which is generative AI and large language models. And if possible, I will speak about the current research scenarios like clip or blip, if time permits. Maybe if still time is there, I will look at the ethical issues or limitations, etc. So this is a broad talk on to introduce you to the current aspects, and it's not technical at all, but rather to educate you on the ideas, core ideas that form the foundations of this technology. So let's move ahead a little bit. So the first thing we should, in order to learn, if you're learning artificial intelligence, you should have an idea about how human intelligence works. So it's a human. All of us are gifted with these 5 senses. You have you can hear to sounds, taste things, touch, maybe smell. You can see. These are the 5 things, basic sensory organs that we have, and these things are connected to our brain. These 5 sensory organs are connected to our brain in such a way that we see signals. Okay, let me put the presentation slow. Okay, the signals from these sensory organs are sent over a nervous system or a set of nerves to your brain, and inside your brain, these signals which comes from various external stimulus is processed in such a way that the brain responds with instant actions. So while processing this information which is coming from outside, brain also uses its previous experiences. Say whether this has seen something, if you're seeing as an old acquaintances, the brain immediately remembers that it has seen some, say, 10 years back, 5 years back. And then, so that information is also added to the stimulus that brain got, and then process it. So this is how you process your information. The brain processes your information. And the brain can do many wonderful things. So it has a very good discrimination capabilities. That means it can recognize things, it can recognize people, a lot of things it can. See, depending on the stimulus as well as what it has learned earlier, it can find out, it can discriminate a lot of things. Also, our brain has a creative capability. There's a creative aspect also, where you see the brain actually can imagine and make things out. So see, we are trying to emulate this wonderful biological mechanism through artificial intelligence. That is how the idea of artificial intelligence started at the beginning. Now, so in order to understand this brain, our human brain, we need to look back how the human brain achieved all these capabilities over the say maybe long years in which humans became humans. So in order to understand that, say you have to look at some amount of history, or historically how humans became humans, or how our brain becomes a supercomputer. So in order to that, you see the Earth has an expected some kind of a age of say 4.54 billions, and see, as the life in our Earth appeared some maybe 3.5 billion years ago, or single cell things, then it slowly produced. I mean, there was an evolutionary process, and at some point, see, the brains appeared in the species that are seen on the Earth. Somehow, at some point, brains started to appear, and maybe the brain slowly evolved into bigger and huge, potentially powerful mechanisms over the years. And out of, if you see the evolution of modern humans also, the human, as of now, we are Homo sapiens. The Homo sapiens appeared around 2 lakhs or 3 lakhs around that. But there were ancestors who were also intelligent people. So there was a sort of steady growth of intelligence among human beings. And so around 70,000, 80,000 years ago, our ancestors were a small clan somewhere in Africa, maybe that red area that is marked here. And slowly we invaded the entire world due to the capacity for brains. So if you see this, as time progressed, the earlier humans, say maybe 70,000, 80,000 years ago, they were just traveling nomads. They were just moving around and collecting things and eating. And slowly, as time progressed, say if you can see this in this picture, it's clearly, say earlier they were foragers or people who collected things and ate and slept somewhere. Slowly, we started building tools, and maybe humans invented books, maybe computers, then all this. Now I think we are all in the last line where we have mobiles, where we are connected, we have all these kind of modern facilities, transportation, communication, etc. So there is a huge amount of knowledge also. So this knowledge has been stored somewhere, there are several mechanisms of storing knowledge, but we have to think of, we have to consider this sort of knowledge also while thinking about human intelligence. Now, we need to emulate this human brain, which has evolved over say 2 or 3 million years, and which can use the collective knowledge it has, the human race has accumulated. So our aim in building AI systems will be to emulate this brain. Now, see, if you look at a human brain, it has several capabilities. See, it can learn. See, the human intelligence, there is something called learn. So you can teach also. That's why most of the teachers are here. You can teach people. You can learn. Also, you have the capability of reasoning, depending on what kind of a situation you are in. You can reason. If you're in the middle of the road and there's a huge amount of traffic, see, you take intelligent decisions of driving. So whether to turn left, turn right, etc. So there's a huge amount of reasoning power associated with our human brain. Similarly, you can perceive things. See, if you're driving on the road, you can perceive that some of the fellow drivers may turn left, turn right, etc. So depending on the situation you are in. So this kind of perception is very important. Also, another thing is that humans can understand language. This is also a gift that Mother Nature has given us over the years. We have developed several languages with which we can communicate. And finally, we have all these feelings. The human brain can understand feelings. When you touch a dog, you will have some feeling. When you touch a rock or a table or a mouse or a computer, you will have another kind of feeling. So these are the capabilities that we are going to build using artificial intelligence. So with this aim, with this target set, see, humans started developing artificial intelligence somewhere in 1956. So that is a beginning. So at that time, it was thought that you can very easily simulate a game in brain with computers. But almost 75 years passed since the beginning of the first artificial intelligence conference, and we are still nowhere in many of the fields. I was mentioning there were 5 senses that we have. Out of that, see, we have some progress on speech and text-speech related things. See, we have reasonably good progress also. I will say that on speech. Say we have all kind of speech to text, text to speech, or speech-to-speech kind of transformation possible. So we have done very good progress in speech things. And as regarding vision, computer vision, and which corresponds to human sight, we have some progress. We can recognize people, we can recognize objects, etc. But still, to understand or fully describe a picture or a video is still difficult for AI right now. But I think we will be improving very soon. And for the other facilities, we are nowhere. AI is nowhere near human being regarding smell or taste or even touch. So there are researches going on in these directions also, but we are nowhere here. Now, let us come to the actual things that we are going to build for AI things. At present, there are two kinds of AI systems being developed. One is called discriminative AI, and the second one is called generative AI. See, earlier, maybe up to the beginning of this century, maybe 10, 15 years, up to 10, 15 years, most of the researchers were focused on building discriminative systems. So if you look at this picture, these two pictures, you will very easily understand the difference between discriminative models and generative AI models. The discriminative AI models, we will try to, if given a situation, we will try to discriminate between things, whether this is a dog, whether this is a cat, or whether somebody known is in front of you, whether the owner of the phone is opening the in front of the phone and trying to open the phone, etc. That kind of systems were being developed for a long time. And maybe, say, within the last 8-10 years, people have started building generative models. Generative models can be very easily compared to something like a creativity of a human being. For example, if all of you are asked to draw the figure of a cat or a picture of a cat, your brains will think of all the cats that you have seen so far. Maybe I'm nearly 60 years old, and over the past 60 years, I have seen thousands of cats. So if you are asking me to draw a cat, what I will do is I will think of a cat, and there will be some kind of a perspective or a rough draft in my brain regarding a cat. It has two eyes, a sharp ear, maybe some whiskers, some kind of a shape, some color, etc. So thinking about that, I can draw a cat on a sheet of paper from my mind. This is the kind of AI that we are trying to do with generative AI. So we will come to it later when I speak about large language models, etc. We'll look at it again. So anyway, in both cases, our aim is to teach computers to behave in the same way as humans behave. So in order to achieve this, the researchers initially looked at, so in order to simulate or emulate a human brain on computers, the researchers looked at how you teach humans themselves. So for example, if you have a kid, or some of you might have kids, or some of you have your friends, relatives, younger siblings, etc. Then, you teach people in multiple ways. You teach them. You tell them that this is a label like this. This is a cat. This is a car, or this kind of labels you will give. Maybe you will teach. They will be taught from your teachers, your parents, your peer group. A lot of people, a lot of things contribute to the learning of a human being. Now, in order to simplify this idea, so let us look at how you are going to teach a very small kid. So in this example here, I'm trying to teach a kid to distinguish between, say, cars and buses. So what I will do is to teach the kid to distinguish between a car and a bus. I will show different models of cars, say, just like this. Say, you can see example. The kid will each time I will tell the kid this is this particular type of car, this is another car, like that, and then I will show him another set of buses in different positions or maybe different views, etc. So that after some time, the kid will learn. The kid will learn how to distinguish between a bus and a car. So what he will do is, see, if he is shown this one, so which he has never seen, he will his brain will think of all the vehicles he has seen, and he will immediately arrive at okay, this looks like a bus in front, maybe side view or something. He will definitely say that this is a bus. Similarly, our brains can recognize this also. See, for example, here you see those from Kerala will understand the situation. This is a bus which was driven into some stream somewhere near your college, somewhere there. I think this accident happened somewhere near the Aruvithura itself. And our brain or a kid can very easily recognize this, even though this bus is not fully shown. But for the computer, it is a very difficult problem. So because if it is trained with the full size pictures, a partial picture like this will definitely is a difficult problem. So maybe this is another thing. See, if a kid can very easily recognize this as a bus trying to fall into a gorge or something, whereas it's for a maybe for computer, this may be a difficult problem. So kids also, humans also run into this kind of issues. See, maybe if you show this to a kid, it's a small, it looks like a car as well as a bus. Some portion looks like a car, some portion looks like a bus. So the kid will make an intelligent guess. Maybe he will say that this is most probably this is bus or car. So most probably this is a bus. He will say that. So if he makes a mistake, what will the parents will say that this is not a car. This is this is not a bus. This is a car. So somebody will correct you. So in fact, our learning sequence is somewhat like this. We will be trained. A kid, as a kids, or even as a human being, we undergo this process. We are always being trained in new things. That is what right now you are also doing. So you are also being taught something by me. So that's a kind of a training thing. And then there is a validation in which see the things you learned or you have been taught is tested against unseen data. So you just like the bus the kid has seen. So unseen things are shown to the kid or even human who is learning, and then he will make an intelligent guess about what it is. So if he makes a mistake, we will retrain it. This is our learning cycle. So the modern AI systems are basically based on this cycle. This cycle we are trying to emulate on computers. So let's see. Now we as humans, when you are asked to recognize between a car and a bus, what we did was we looked at the car and then we looked at the bus. So there are some distinguishing marks or distinguishing features which actually makes things different. See, some of the features are different for the bus as well as for the car. So what we will do is we generally learn from features. For example, this is how you recognize faces. See left on when you see my face, say maybe most of the people are seeing me for the first time. So when you see my face, you will mark certain points on my face. See, these are my distinguishing features. Maybe my eyelids, maybe my nose, my mustache, or somehow there are certain features that we keep on distinguishing. Now, inside our brain, now you think of this situation. See, when you see this particular person, when you yourself are seeing me, these features are sent from my neural sensors in my eyes to my brain. So as some biological or electrical excitation, and these things are remembered. Now for the computers, So when say the same thing can be achieved using a photograph. Maybe computers can take a photo of my face. Maybe it can grab this screenshot from here and take a photo. And then if you want to recognize this Sunil, you need to compute. So what we will do is you need to, all these features, you need to compute, convert into numbers on computers. So this essentially, all these numbers that I have marked, A, B, C, D, etc., they are measured or somehow they are converted into numbers, and my face is represented on a computer as a set of numbers. So these numbers will is what computers will process, or modern AI systems will do this kind of number processing based on the features of various objects it is intending to do or recognize. So the first thing any AI system will be doing is to get inputs as features. So it means that will be a huge set of numbers. Say, for example, see this particular picture. Maybe I have marked only very few number of things are there. It can have, say, thousands of features. Maybe say 1,000 feature can be there derived from here, and those numbers are. Yeah, what happened? PPT is not moving. Yeah, somebody said. Yeah, this is where I'm. Are you see? Oh, it's not moving.
Slide 27, sir.
Slide 27 stuck.
Yes.
Yeah,
Yes,
wait.
sir.
Oh, stop sharing. I'll reshare it. Something happened. Wait. Hopefully, if there is an issue, just tell me. So what I was telling was that all these features have to be represented as numbers for a ML machine learning algorithm to understand. So, so let us see, once you represent everything as numbers, so how do we go about? So let's say for that, I will show a toy example where I was talking about some small problem in which you have cars, you have buses, etc. We'll make a toy example of that and say build some of this say toy feature and try to see how an ML algorithm or AI algorithm should learn. So for that, so suppose we want to distinguish between this bus and a car problem. So some of the features that you can use is number of wheels, size, etc., etc. Some of the features you can think of like this. So I hope this is visible, no? Right? Are you able to see the table?
Yes, sir.
Yes, sir.
No. So let us assume that we have just three features. Just three features. So in practice, just as you showed your face, there will be thousands of such features. But in order to understand the exact idea of how a model should work, I'm just limiting this toy example to just three features. So there is a weight, number of wheels, number of doors. So we have collected data for, say, four different cars. Similarly, so I have collected data for say four different buses. Say Tata has this kind of number of weight, number of wheels, number of doors, etc. So now you can think of these features as independent things. See, it means that weight has no relation to number of wheels. Similarly, number of wheels has no relation to number of doors. So there are independent features. The features are not dependent on the other one. So one feature is not dependent on the other feature. So it means that they are independent. So assuming that these features are independent, you can represent them. Say, since I have only just three axes, you can represent them as three different directions in a space. Say, for example, you can represent the weight in x-axis, number of doors in y-axis, and some other things in the z-axis. See, this is because these weights are independent. So those who have studied some linear algebra may think of it as basis vectors, independent basis vectors, which represents the space. So which spans the feature space or the space of this particular thing. So since we have just 3 features, we can just mark these points. Each of these cars can be marked. Say, maybe I can mark all my cars somewhere here. Say they are all similar. They will be all somewhere here as a cluster. They will appear. Similarly, since you have a set of buses, they will appear as another cluster somewhere here. So this is how you convert from your space or the actual features to a feature space. So in practice, there will be thousands of such features, not just 3. In a real world scenario, there will be such thousands of independent features. For example, if you think of the face has a lot of features as I showed. So each of these face will be one axis. So you cannot visually represent it here, but in terms of the linear algebra thing, which some of you might have studied, see, it means that if you have 100 features for a face, each face will be a point in a 100-dimensional space. So each of the spaces will be one axis, and they will be independent. You can represent any point, any feature point on one axis, and your independent instance of your face or a car, whatever you are thinking of, they will appear here as a point. Now, see, this is very easy to distinguish between X and Y or buses and cars. What you need to do is to divide this plane into 2. This particular 3D space into 2. You can draw a plane. You can distinguish between 2. So, for example, say maybe to distinguish between buses and cars, you need to draw this black line. This black line actually represents a plane, which I cannot. My drawing skills are not very good. So what I have done is, say this represent a plane which splits this 3D thing into 2. One side you will have all your buses. The other side you will have all your cars. So once you know the equation of this particular black plane, which separates out these 2 things, it is easy for you to distinguish things. Any new bus will be appearing on the one side of this plane, and any new car will be appearing on the other side of the plane. So in order to distinguish between these 2 things in a single feature space, in a feature space 3 features, you just need a plane which has just 2-dimensional thing. It's just a 2-dimensional plane. It can split into these 2. So now you think of your faces. Since your faces having say 100 features, since you are having 100 features, so a face recognition program which recognizes 2 people, just 2 people, it should have it should divide this 100-dimensional space into 2. One side will be the photographs of one person, the other side will be another photograph of the other person. Now there are challenges to this. See, for example, this is what I meant. If a new car will appear here, similarly, a new bus will appear. See, which is depending on the features, it will appear somewhere here. Now there are issues like to find the best line, best plane which separates out these 2 axes. So this is basically one of the problems that AI researchers will find out. Will work out. So this is the idea. So you have a feature space and you have some separating plane which splits the feature space into different things. Now let us come to an actual problem. In an actual problem, we say in the toy problem we have just had 2 things. One bus and one set of cars. But in a real world scenario, you need to distinguish between hundreds of objects, not just 1 or 2. Say if you're recognizing faces, you should recognize between thousands of people. So you need to have a complex mechanism of splitting this feature space into multiple compartments, where each of these persons will have a separate area. So that is where your AI models will come in. AI models will come in. Both discriminative as well as generative models are based on this idea. So we will have some mathematical thing, mathematical function, which separates out your feature space into multiple compartments, which people can use to distinguish between things. Now let us look at the discriminative and generative model. So we will come to it later, a little bit later. Now the problem, see, learning from
Sir,
problem.
lights are not visible now.
Again, slides went off.
Yes, sir. Please scroll down, sir.
Which one? Yeah, up to what point you could see? Just a second. Okay, it's scrolling, right? Oh, yeah, it's scrolling. No, I think I need to see this for myself here, full screen. Okay, right. Can you go up? Yeah, this is where we were. Yeah. Am I audible?
Yes, sir.
Yes, sir.
Yeah. Now, I was mentioning about facial features. So from those numbers, computers need to distinguish between all these things. See, in a glance, you can very easily distinguish between each faces, whether the person is angry, whether the person is smiling, etc. We can very easily do. But for the computers, it's a very difficult problem. So because I mentioned that the model which we are trying to build, the AI model which we are trying to build is essentially a mathematical function which separates your feature space into multiple compartments. See, all those features which are appearing, say near, say this smiling face will be smiling people smiling. The angry things will be angry nearby. So in such a way, you have to compartmentalize your feature space. So this is not an easy problem. So what people did was to build complex mathematical things earlier. Say earlier things in the beginning, people tried out different techniques like nearest neighbor classifier. You might be learning, some of you, to see things like nearest neighbor classifier, support vector machines, neural networks, etc., etc. A lot of different algorithms were tried out. And at one point, it was seen that neural networks. So this is the next slide. Neural networks. See, brain. Say just go up once again. Just here. So our brain has a neural network structure inside. So as people looked at how human brains functions. Human brains have a lot of neurons inside the brain. And these neurons are interconnected among themselves. So when you have an excitation, when you see something, some of these neurons are excited, or some of the strength between these neurons are sometimes strengthened, sometimes weakened, and this is remembered for also. As something for the future memory, etc., is marked in the your neural network. So people tried out neural networks somewhere in maybe 1970s, late 1970s, etc. People, the scientists who were doing research, tried neural networks, but at that time, the computers were not very powerful. Computers were very less powerful, and to build big neural networks, it was not easy. Then, to train these neural networks, you need huge numbers of data. The element of data that is required to train a neural network was so huge. So people actually tried out other methods in 1980s, 90s, etc. Maybe up to 2010, etc. Up to 2010, people were trying out. Stop that thing here. Don't move the slide. People tried different techniques, but ultimately the neural networks algorithms or this method of imparting intelligence to computers using neural network was reinvented somewhere some 15 years back. When this happened because of just two things. One, the present day computers are extremely powerful. You can just think of your mobile phones. 5 years back, your mobile phones were maybe taking pictures at 14 megapixels or 10 megapixels. Now you have something like 100 or 50 megapixels, good quality mobile phones with you. The computing power has increased so much during this past 10, post 2000, so that the computation engines with the neural networks are possible these days. Also, to train these networks, you need lots and lots of data, which is again available freely on internet or very easily on internet. So what now we do is that instead of say building some arbitrary mathematical functions, we train a neural network using neurons. So we can just move to the next slide. Justin, can you move? So inside your neural network, this is the typical artificial neural network. So I have marked these things in Malayalam. Sorry. So I was speaking to some of the school students where I wanted all these things in Malayalam. So see, most of you should be familiar with these things. See, a neuron inside your neural network will be model some like this. There will be inputs. There will be inputs x1, x2, xn, which corresponds to the features of the face or whatever you are doing. So these are the input features, and then there are set of weights for each neuron, and which is then summed up. Input multiplied by the weight is summed up into using some summation mechanism. The mathematical notation is clear. Then there will be a final activation function, and finally there will be an output. This is a typical mechanism for a neuron. Okay, you can just move to the next one. Yeah, this is a similar a comparison between a real neuron and an artificial neuron. On the left side, you will see a real neuron in your brain, which takes input from various dendrites or something called. Then it moves, it passes on after processing to the other neurons. So you can just move to the next one. So in practice, we build a neural network in this manner. So the inputs will be given to one layer, and there will be certain hidden layers, a set of layers which are hidden, and finally you will have some output layer. Your current generation of AI models are built on this idea of neural networks. So you give an input to a neural network, see which are trained then, and then you will get an output. You can just move to the next one. So this idea of training a neural network, that is something which people always got confused. So in order to explain that, so you can look at this picture. I will explain what exactly training is. You see the mechanism. See on the left side, as input, we have 3 different water tanks. You see the different water tanks. So each water tank has a particular colored water inside that. Say the green water tank contains green colored water. The blue one contains blue colored water, and maybe the other one contains that color. And see, these tanks are connected from each tank. See, there are 2 hidden tanks. You see that hidden layer? The water tanks are input. There's a hidden set of tanks. And then there is, from the hidden tanks comes out a final tank from where you can take water outside. So there's a tap which can come out. Now, if in each connection between tanks, you see that round valve there. There's a valve which can be turned round left or right, so that you can control the amount of water flows into the next thing. Now, given this setup, if I ask you to produce, say, yellow colored water from the top. So you know that your inputs are green, yellow, and purple or some what is that color? Magenta color or something. Then you are asked to build, say, yellow colored water. So what you will do is see each from you will try to turn the valves in the just before the last tank. So the final layer, there are two valves. You will just try adjusting those valves. So you can just bring it as as nearly possible to the desired color, but you cannot reach the actual color. So what we will do is that we will adjust the valves in the left of that. See, which connects to input tanks to the hidden valves. So again, we'll turn around. So when you turn around, maybe your color on the final stage will again change. Your setting may have to be readjusted. So this process you can do many times. So you can adjust this weight, then again the left side, and you go until you find out a proper combination of valves, so which produces this one. So this is how a typical neural network works. Now, if you go back, just go back to the back side. One more slide. So here, see, if you see the input is your face, the output, maybe you have to distinguish between me and somebody else. So given the input, so these there are weights in between the connections. You can adjust those weights so that when my photograph is given, so this flag is that this particular person has come. So somebody else's photograph is that person can be flagged. So this way, if you can adjust these these weights, just come down to the next one, just similar to these valves. Now, in order to build a useful system, you need to you can go to the next one. You need to say this is a typical one which shows number recognition, a typical problem which we teach as a first step in ML classes. We'll say handwritten number recognition, MNIST data set. So we will have some 768 pixels of corresponding to each of these one, and we need to find out which character is being written. So this one, given this particular number 4, it has to give number 4 there. So initially, you assume that you have random weights in the network. You give number 4, something else will light up, some other thing will light up. So we will adjust these numbers so that when you give 4 will light up. Then you will give another number. Then something else will come up. So this you have to repeat for all these characters many times. So lots and lots of times, so that given any character, say 9, 10, whatever it is, 9, 0 or whatever characters, this will be properly done. Okay, you keep it there. So the problem is that this network, such a network, is very huge in nature, which if you want to do any actual real world job, this network will be very huge. But you need to train this on computers. So here comes the power of graphical processing unit. You need in order to train any neural network, you need huge or very huge graphical processing or computing power, which is probably available from our current generation of GPUs. So you can move to the next slide, Justin. Now, see, these models, these AI models, generally don't give the direct output. Instead, they produce probabilities. So if you're given a cat, these models will sometimes predict these are as probabilities. So this, if you given, so assume that this is a model. This is a model which is a neural network, huge neural network, which has been trained to produce recognize the particular animal. So given when you give as a test example, so you have trained this model on thousands of animal pictures. Now you are showing an unknown animal to the model. The model will say that, oh, so this looks, say, 90% like a cat. this looks, say, 5% like a dog, maybe 2% like a tiger, maybe something like that. So this is the typical type of output you will be getting. And from here, you need to choose the best one. Okay. Now let us come to these two models, discriminative and, okay, you can just skip to the next one. So, as I told you, the building your models or training your models from data is a very huge task. Maybe you can keep it there. So to make it clear, I will give another example. See, you need to distinguish between dog and cat. So I have several dog pictures, several cat pictures with me, and I am trying to build a model by placing them on my table. I'm going to place these pictures on my table. See, you understand the scenario. That screen is my table. I will be placing pictures of dogs somewhere, pictures of cat somewhere on my table. And once I have placed one picture, one set of pictures, I need to draw a line which distinguish between these two. Now you can move to the next one. Now I placed one more cat, or maybe one more cat I have placed. Now my original scheme is wrong. I need to change my model slightly. So that sorry, you can move to the next. Yeah, again next. So as and when more data comes in, you need to draw a line such a way that, see, it actually represents the way in which my cats and dogs are distinguished. So this is the challenge that you have to do. So this has to be done not in 2 dimensions, but in n dimensions. See, this was a very simplified model in which you're training, the issue of training, I showed with a simple line. But you can keep the other one. I haven't finished. Yeah, but see, in real life practice, your neural networks should be able to distinguish between thousands of objects. So the size of the network is very huge in the sense it is very difficult to train. It is very difficult to train and build things. So the current generation of models like GPT or maybe Llama, they have maybe trillions of parameters, 1.7 billion parameter kind of things. There are so many neurons are there, and so it is not easy to just turning the valve, but you need the systematic approach to train such networks. So that is why what the current challenges that we have with the AI models right now. So you can move to the next one. So in order to understand this, see, you need say this kind of models. You need to, one set of models, you need to distinguish between cats and dogs. Say you need that is for classification. Then you need models for localization. See, on the picture, here is a cat. Here is the object. Here is a particular object. Say maybe you need the idea of cat, segments of area where cat occupies. This kind of model you need to build. So it's not an easy task these days. With simple computers, you need a lot of computing power. You need a lot of data. You can go ahead. Next. Yeah. Yes. Somebody is speaking. Now, see, this kind of neural network mechanisms were being tried out. Maybe this started again somewhere in 2012. That period. See, people started building a lot of models using something called convolutional neural networks. So I know many of you are experimenting with convolutional neural networks, etc., etc. And a lot of very good systems were built. Say maybe for face recognition, maybe for object recognition, segmentation, etc. A lot of people built a lot of models using see the neural networks and some a technique called convolutional neural networks. But somewhere in 2070, there was some very good improvements or very good research improvements in which people, one set of researchers from Google introduced an idea called a transformer model. It's again, transformer model is again a set of big neural network which can do a lot of tasks such as language translation, language building, etc., etc. So their idea, the large language models or language models started using this transformer architecture. So the idea behind large language model, I can summarize on this slide. See, you look at this slide. The idea. So we were doing a lot of classification, a lot of things with all these earlier neural network models. What the developers of large language models tried was to model the spoken language that we are using or written language that we are trying to speak or write. Say, for example, I am speaking to you right now. So I have been speaking to you for, say, 1 hour almost, no? Right. Almost 1 hour. I've been speaking. Now, what will be the next word that I will speak? Can anyone guess? No, you cannot. You cannot guess what I will speak next. But my brain has an idea of what to speak next, because I have been talking to you people for, say, 1 hour on AI and AI-related technologies, and I need to speak for about half an hour on this stuff again. So my brain has an idea of what to speak next. So this idea, whether you can capture this particular idea into a neural network or a computer, you can actually predict it. So the idea of large language models was to predict the next word that is going to come. For example, if you look at this slide, so again, look at this slide. See, I have a partial sentence. The sky is. I am giving this to a neural network, a huge neural network, and ask it to predict what is the next possible word that can appear in the sentence. The neural network, this particular neural network, was initially trained with lot of text examples. It has seen, this network has seen lot of text during training period. This is a trained neural network. I want to emphasize that the neural network I'm showing it as LLM is a trained one, which was trained on loads and loads of data from internet, which contain text. So it has been shown a lot of text, and it knows what is the most probable words, list of probable words that can appear next. So when I ask this LLM that this is a partial sentence and I want to complete it, so it will give you the set of possible words. So the sky is, say this is, I have written some of them, but there is a very rare chance that sky is cat, sky is dog. You won't write like that. So in its previous training in time, the LLM has seen what are the possible things that can happen, what is the probability, how many times it has occurred, and it has learned that. So this will generate the next word or a set of words which are most probable from the given sentence. This is the idea behind our current LLM explosion. Basically, you see, the sentence that I gave is called a context. From the context, it can predict the next one. Maybe there will be something else behind that. See, if it's a poem, it can be maybe some like blue or some kind of color. If it's a weather advisory, it can be cloudy. The sky is cloudy. Probably if I am describing a weather report. So that is what I was telling you. My brain responds on the context of speaking to you. Just like that, a neural network can be trained to respond to this particular context in which it is sitting. So this is how you choose you predict next. Now, the first question you will be asking. See, there are say 5-6 possibilities. Which one you will choose? Which one you will choose? So there are strategies for that. There are strategies for choosing this weights. So maybe if you want very authoritative thing, maybe very very formal report kind of thing, you will choose the most probable one. And if you want some creative kind of stuff, maybe if you are writing some poem, you can maybe choose between any of them. So this is why your ChatGPT gives different answers each time you ask the same question. So it is given the context, and it is predicting next word. You can see that if you are using ChatGPT, see, it will start producing one by one each one. So if you run it again, so it has learned that the prompt that it gave you back, the result answer is not good. So you should choose something else. So it can just choose another one. So there are issues also for this. The LLM can hallucinate. Someday, if you make a wrong choice, it can give you wrong answers. That's why there are issues with LLM. So you can just move to the next one. Yeah, this is the kind of large language model or the idea of large language. And you can just again move down. So this is how the GPT data and parameter size exploded over time. Maybe parameter count. Say if you look at this, the 2018 we had a very it was something like a million, and in 2024 we have our parameters or number of neurons is something like trillion, 1.7 trillion or so, and also the number of data size on which it was trained. The older versions, this is why newer things are coming up. Okay, you can move to the next one. So this one, okay, let us stop the LLM. Now, LLMs or the modern neural networks which I spoke about right now, or the LLM, they are to generate text. And the other thing that you want to do is images. Here comes something called diffusion models. Diffusion models, which this is how, using this, you create images. You see, some of you might be seeing how Gemini or some of the models like DALI, etc., generates these images. When you say that you generate a butterfly, it generates a beautiful butterfly. This particular thing is an AI generated thing. So in order to understand how they work, I will explain that the diffusion model and close my talk. Maybe it's already, I think, my 20 more minutes are left. So in order to understand the idea behind how AI generates images, let us look at this picture. On the left side, you see a butterfly. On the middle, you see something called a noise. This is a noise picture. See, a noise is something which when you see on the TV, when the lightning comes, you will see white spots, etc., etc. So this is a typical. That's a typical noise that happens. So this is a particular noise, something called Gaussian noise. So there's something called Gaussian distribution. You should look at it if you're seriously trying that. So there is something called a noise here. So if you add noise to a picture, you see the right thing happens. The picture on the right side emerges. You are just adding some noise to a picture, and you're blurring it. You're blurring it. You can go to the next slide. Now, look at this. So I have done this once. I've added noise to this once. Now again, to the noisy picture on the top, that is on the right side, that I have brought down one step down on the left. So the one on the right on the top row is same as the second row, first the left on the second row. Again, I'm adding noise. I'm adding noise. So again, it will go blurring. The blurring will improve. I mean, it will blur. And slowly, if I add more and more noise, you look at this. I'm adding more and more noise. The picture will fade. The picture will fade, and finally, it will. The picture and noise will become indistinguishable. You cannot distinguish between noise and vector. You can just move to the next one. Yeah. Okay. You go up again. Go up again. Just go up. No. You went down. Up. Yeah. No. More like go. Yeah, this is where we started. Yeah, fine. This is where this is where we are now. So I am successively adding noise to pictures. So if I add this, say 1,000 times or 10,000 times, my picture will become so blurred that I cannot distinguish between the noise and the picture. So it can reach that stage. So now let's move to the next slide. Now, in the above process, the first step was you think of the first step. So we added noise to a butterfly to get a noisy image. The original image is on the right, noise in the middle, and the noisy image on the left. Now, if you subtract this noise, if you subtract this particular noise from the noisy image, you will get back the original one, right? Hopefully, everybody understood the idea. You can move to the next. Now, assume that we have a very, very, very noisy picture. It's just undistinguishable thing. There is. So if you can somehow remove the added noise, we don't know what is added noise, but somehow if you figure out the noise and remove it, successively, if you can remove this, see, you can recover back the original picture. But the challenge is to find out what noise was added at each step. What noise was added at each step in finding out, in blurring the image. If you can find out that, you can just get it back. Okay, now we go to the next one. Now, this is a typical noise. There's nothing here. But you can take back. So if you want to create if you want to create the picture of dog, you can take back some noise which was added to a dog's picture. Say you assume that you have a dog's picture and you added noises successively, say 1,000 times, 10,000 times, and arrived at this. You are assuming that. Now, if you can take back those noises, those added noises, you can reach that dog's image. So it means that from this noise, you can remove noise in such a way that any picture can be built. This is the basic idea of diffusion modeling. Come down. Okay. Now, ഒരു സ്റ്റെപ്പ് കൂടെ മുകളിൽ ഉണ്ടായിരുന്നില്ലേ? ജസ്റ്റ് ഒരു സ്ലൈഡ് കൂടെ ഉണ്ടായിരുന്നില്ലേ ഇടയ്ക്ക്? Okay, this one. Okay. Now, when you say this a stunning picture of some lady looking like Aishwarya Rai or something, say this is what you give to your ChatGPT also. So what exactly it does is that it will reconstruct a series of noises which can be subtracted from the original noise, some noisy image, some noise, and which can reach your target image. So this is the idea. This is the kind of modeling that is being done. So for diffusion modeling. So you just come down. You can generate this kind of beautiful images by just controlling. You're just changing away the noise. So this is not an easy task. This is not an easy task. You need huge computing power, huge amount of maths behind this, which noise to remove, etc., etc. This is just a probability equation, a series of probability equations which you are playing with. So maybe the diffusion model is something which is being still explored. You see that a lot of things like deepfake are being built using this. So people are trying to control the noise in such a way that the face across images, if you're creating a video of a beautiful lady, across the images, they should look like similar. So it's not an easy task. People are trying out different things and building things. Okay. Now, I think I can, how much more minutes we have? 50. So I will just skim through some of the things which you should look at. So these, okay, just go up. NLP, natural language processing, just go. This is one area where there is a lot of impact of these newer AI algorithms, LLM models, etc. A lot of things. You see, the NLP thing, natural language processing, was there right from 1970s. Lot of things were tried out to teach computers the language, translation, and spell check, etc., etc. And all of a sudden, almost all of the classical techniques that people were using have been overshadowed by LLMs. So if you look into, say, ArchiveX or some other good research journals, you will find a lot of things, older NLP things, NLP algorithms are being replaced by LLMs. So those who are doing the research area on NLP, definitely there are a lot of scopes. There are a lot of ideas you can try out. You can try out Indian languages. You can try out OCR. You can try out sign language. You can try out a lot of things. You can try out. All the classical problems are still there. All the problems you can try out using LLMs. So it's a very good research area. A lot of people are working. A lot of new products are coming. And it is easy for you to build also. Okay. So you can move to the next one. And computer vision is another thing people are working on. So even in computer vision earlier, so I was trained in computer vision earlier and during my PhD, as well as my other stay at IIT. I was extensively working in the vision lab, and we were all working with older techniques like SVMs, etc. Now the CNNs, convolutional neural networks, and large language models, etc. I mean, these diffusion models, they have taken care of everything. My students now work only on these models, all these vision transformer models, etc. And there are a lot of opportunities in which you can try out. You can try out emotions. You can try out sign. You can lot of things. You can. There are a lot of things yet are there yet to explore. Also, the correlation between text and speech. This is another area of very interesting research. There are algorithms like CLIP, CLIP. You can just search for CLIP and blip. These are two different approaches to match between text and images. Say, whenever you are playing a dance or something, some kind of an activity, maybe if you are running or if you are acting in a movie, etc. There's a vision part, there's a speech part. So recreating or correlating these two is another important thing. So there are algorithms like CLIP and blip, which people are working on. So some of you can very easily work on. And there are some very good courses on Stanford also, which explains these ideas. So I have just recently seen, I think, CS230N or some. There's some course where you can go through the latest things on vision transformers, etc. And maybe you can just move to the next one. Yeah, there is a huge amount of data requirements. So that is another area which you can try out. You can contribute to data. See, as a researcher, data sets are in very huge demand. You can build data sets. Maybe you can language data sets. It's possible. You can build vision data sets. You build a data set and you work on this. See, some of my research area basically we work on gesture, dance gestures, or dance mudras, etc. We have built an extensive data set, both video as well as images, and we work on those data sets. Say something like 1 lakh images, etc. It's very common people to work. See, earlier people used to work on 100 images, 200 images in data set. The size of data set actually matters, and you should work with, say, a huge amount of data. Okay, just go ahead. Maybe load of data. Okay, so what you need in order to work decently in your lab, you need a very good computer. So see, this is a typical GPU that you can buy in the market. GPUs are available in different categories. So the one that you can afford as a researcher or your college can afford is the normal consumer grade GPU, like this is 4090. I think 5090 has come. We have one 5090 with us. See, this is a typical GPU with which you can try out some of these ideas, some of these models, etc. But if you want a real work, you need a bigger GPU cluster like H100 or A100, which goes around something like maybe 30 lakhs, 40 lakhs, etc. That kind of GPUs are needed for huge work. But this is something you can try out. Maybe I will stop here with a few more things, just mention a few more things. Many of these people working on AI models, it is not possible for us to work with models like GPT. I mean, to build from scratch, we will not have sufficient data or sufficient computing power to build a clone of GPT or some of these models, big models, you cannot do. But what we can do is that you can take such models. Such models, they say, is having 1.57 trillion parameters. See, there are scaled down models which takes a part of this one. It's called if you go to a site where you can see download models, you will see smaller models. So based on the bigger trained thing, you will have 1.5 billion parameter model, maybe 14 billion parameters. Smaller models are available. Don't change this one. I keep it there. There are smaller models which you can download and experiment with a smaller GPUs. Smaller GPUs. Using smaller GPUs, you can try out these kind of small on your lab. So this idea is called fine tuning. The idea of taking a big model and teaching on your data is called fine tuning. You can take a open source, open weight model from Hugging Face or Kaggle, download it. You can train on your own specific data set, and you can build a new thing. You can build things like that. Similarly, there is something called a RAG, retrieval augmented generation, which means that see, some of these models, original models like ChatGPT, they are time limited in the sense that these models were trained only up to, say, last March, maybe 1 year back. Now we have a lot of data coming in later. So you can retrain using that data. You can show these models these particular data that we have, additional data or current data, and retrain it. For that, you don't need a very big GPU. You can try smaller GPUs and retrain. So this is where you, as a researchers, as a students, you can try out. So don't jump and try to build or clone GBD or big models. Get a scaled down version of them and try to implement a lower thing on your own data. Also, there are something like student teacher model, etc. A lot of new things are coming up. If you look at ArchiveX or some GPU, AI related sites, a lot of newer parameters coming up, and maybe new fresh things are a lot of new research areas are coming up. Okay, you can just move down to the a couple of more slides down, Justin. Yeah, go up again. Just go up. No. You are doing താഴേക്കാണ് പോകുന്നത്, മുകളിലേക്ക് പോകും. അവസാനം ഇട്ടിരുന്ന സ്ലൈഡില്ലേ, എന്റെ തൊട്ട് താഴെ ഞാൻ അവസാനം ഇട്ട് നമ്മൾ വർത്താനം പറഞ്ഞിട്ടുള്ള സ്ലൈഡിന്റെ തൊട്ട് താഴെ, GPUവിന്റെ തൊട്ട് താഴത്തേത്. അതിന്റെ തൊട്ട് താഴത്തേത് ഒന്നുകൂടെ താഴെ ഇടട്ടെ, ഒന്നുകൂടെ. Here. Now, I will wind up my talk here because there are other things down the stream. I will share the entire slides to you. The remaining portion actually concerns how transformer model works. This is actually a 3-lecture series that I gave to some of my students. So remaining portion explains how transformer works, etc. So you can just take it up, have a look at the slides. So he will give you that. And before winding up, so I put this slide here so that there's a huge amount of hype behind this. So any technology, any new technology is hyped. Whether this is blockchain, whether this is .com or whatever technology that has been over the years, people make a big hype. They say that AI will solve everything. AI will not solve everything. I'm very sure. So there is a huge hype, and now we are on the peak of that hype. That is why every college has AI courses. Everybody is running after AI and disregarding the basics. So this will stop. Today or tomorrow or in very near future, this will collapse. This will collapse and there will be low. People will discard everything. So those who are students, learn your fundamentals and make sure that you are ready to switch to any other computer science field or any other fields when this collapse comes. So once this collapse comes, this is a general hype cycle, Gartner's hype cycle. This is a typical hype cycle of any technology, that new technology that can happen. This is prepared by Gartner or a consultancy company, and they say that after some time this will become mainstream. Just like your spell checker, never look at the dictionary for the spelling. Spell checker is built in. So just like that, AI will be built into your tools, and you will be using them as usual. So wait for that plateau when everything settles down, everything is AI enabled, and make sure that don't jump into this one thinking that everything is AI. So this is not going to happen. Or even though people are after AI right now, after some time they will reach. Say, just think of blockchain. So people 5 years back, everybody was after blockchain. Now I think blockchain has matured into a technology that people can use, but that hype is gone. I suggest you to read. There is a very good book called AI Snake Oil on the Amazon. There is a book called AI Snake Oil. I suggest everybody to have a look at that before jumping into AI bandwagon. AI is just a technology, and just like any other thing. Definitely, it will have a lot of impact and a lot of things in a way in which we live. Just like when mobile phones are impacting us, AI will be impacting you also. I think I have only 1 more minute for my talk. So I think I will say thank you, and maybe I can take a couple of questions if you want. Otherwise, I will say call it a day. Bye. Okay, thank you.
So, dear participants, if you have any queries, you may please ask now.
Fed up with we have 180 participants, right?
Yes, sir.
Is this a free course or there is some registration fee?
No,
Free
sir.
one.
Free.
It's free. So that's why a lot of people are there. Is this adult supported or?
Adult
Yes,
support.
sir. Adult
ACP.
support.
In fact, we sometimes offer at my institute. We sometimes offer summer schools and winter schools on this, but it's not free as like this. We do 3 or 5 days winter school to summer school. You can look for that. We charge decently for this kind of new technology. There are a lot of hands-on exercises also, which we sometimes run this kind of courses in which we teach in hands-on, so that all Python codes, etc., will be there. Okay, thank you.
Sir, one query in the chat box.
Yeah, tell me, read
New
that.
research areas in NLP.
Yeah, what happened? NLP?
What are the new research areas in NLP?
NLP, you see, people are, such NLP, the natural language processing, a lot of new things are happening in the sense that most of the things you are looking for, say, like, say, POS tagging, entity recognition, see, all those people were working on all those things for all languages. See, people are reworking on all of them using these LLMs. So it is very easy these days to build an NLP system. A lot of things are there. See, agentic kind of things are there, so that to understand your speech, if you can see, you can build systems which understand natural language and perform some thing and do your actual work. Those kind of things people are working on. A lot of NLP tasks. See, whatever you are working for earlier, people are building agentic kind of things. Okay.
Sir, one more question, sir.
Tell.
Next booming technology after AI.
What? Can you repeat?
What could possible the next booming technology after AI?
I don't know, because I know only this much. I don't know what is going to happen. Probably a lot of new applications will come, new opportunities will also come, which will integrate things. See, one thing for sure, your computer programming kind of things are dead. So you don't need to program anymore. You can just ask computers to write programs in English language. See, it's called vibe coding. A lot of people are vibe coding. You can build a website overnight. You can build an application, the app overnight without even knowing coding. You only need English. Properly understand the problem and tell what is your requirement in English. That will give you. So the idea of computer programming may be gone, but your computer science will never be dead. You need all data structures. You need all your algorithms, etc., for building things. Newer things has to be done. So those fundamental things will be remaining there, and it will never die. But all these things which people built upon, UI UX, is gone. Any kind of user experience or user interface you can build overnight. Your programming, programming itself will be troubleshoot, some kind of a debugging thing. So AI will write all your program, but you need to put in your knowledge to debug things. So that kind of things are going to come.
Sir, one more query in the chat box.
Yeah.
Any inputs on how common sense reasoning can be taken forward in AI?
See, one thing is that common sense is very rare these days. So what you call common sense is very difficult to quantify, in the sense that the common sense for me may not be the common sense for you. So that your common sense will have definitely a market in future, and maybe some of the systems will find out what your common sense is. It depends on cultures also. See, for us, some of the things like spitting on the road is normal, right? Say it's not frowned upon in many places in India. It's quite natural, but if you go to the West, it is different. So it's just like that, common sense is also something which you cannot very easily quantify. Anyway, thank you. I think I will call it a day.
I think there are no more questions.
Yeah, I
So,
think I will not take anymore. Because I just came up to 2 hours almost I've been speaking. Right. If you okay. Also, we are actually conducting some of the courses for students also in our institute. But you can look at our LinkedIn page for that. We sometimes allow announce free courses for students. Sometimes very cheap, so maybe 100 rupees. I mean, 500 rupees. We run sometimes Python courses like that. You can just look for some of those, especially those from Kerala. You can look for some of our courses. You can look at the LinkedIn page of or either my page or your IC4's page. You can look. Okay, thank
okay.
you.
Thank you,
Shall I-
Sunil sir.
Yeah.
Thank you, Sunil sir, for your insightful and engaging session. Your expertise and clear explanations have given us a strong foundation to begin this FTP. Thank you so much, sir,
So
for your
thank you.
valuable.
Shall I exit?
Yes, sir.
Yes, sir. Thank you, sir.
People are still there. I think people might have left. No, 180. Okay, that's a great number.
There is one more session, sir.
Link not operating. Today, one more session is coming today.
Yes.
Yes, sir. Yes, sir.
Oh, so then this should be pretty heavy, right?
The
Thank
session is scheduled from 6:30 to 9:30.
So one more is there.
Oh,
Okay, then I will exit right now, straight away. Thank you.
okay, sir. Thank you.
So, dear participants, we will now move on to a 10 minutes break. The next session will begin at 8:15, around 8:15 p.m. There is no need to log out. The feedback form has been shared in the chat, so you may please fill out it during this break. Thank you. So, dear participants, next we proceed to session 2, handled by our respected expert, Dr. Justin Joy, Head of the Department of Computer Applications, St. George's College, Aruvithura. Justin Joy received his BTech degree in Computer Science and Engineering from Cochin University of Science and Technology, College of Engineering, Chenganur in 2009, MTech degree in Computer Science with specialization in Information System from Mahatma Gandhi University, Rajgiri School of Engineering Technology, Cochin in 2011, and PhD in Technology from Cochin University of Science and Technology in 2020. His current research interests include assistive technology, natural language processing, and machine learning. Sir is very passionate about free software and promotes its use. Today, he will be delivering a session on programming AI, offering practical insights into building intelligent systems. So, over to you, sir.
Thank you, Swami Miss, for the introduction. And good evening, all. My session is titled Programming AI. So we have already seen that AI is a very general term. So though the title is Programming AI, I will be focusing more on machine learning and specifically the TensorFlow machine learning library. So this is the agenda of today's session. We'll see an introduction. Next, we will be seeing the machine learning pipeline. Then we'll be seeing the machine learning from a hardware perspective. Then we'll see the programming abstractions based on the hardware perspective. Then we'll be seeing how to code for CUDA. Then we'll be seeing some of the popular machine learning libraries. We will see the concept of scalars, vectors, and tensors. Then we will see the major operators and important methods. Then we'll be moving to the dataset class, which is part of TensorFlow library, specifically the data module. In that, we'll be seeing the methods map, batches, shuffle, take, which are very important from a programmer perspective for machine learning. Then we'll see what is TF records and shards. Then we will wind up the session with the major repositories for data sets and models. And we will see an overview of Keras, which is integrated into TensorFlow. So my aim is to give you an introduction to programming from a machine learning point of view. I won't be going into the implementation of the concepts, machine learning concept, but what I will be doing is the very basics of data, how to handle this, and how you can put that into the machine learning pipeline. So this is an introduction which we have already seen. So we'll start with artificial intelligence. We know that it is a technology that enables machine to mimic the human intelligence. Then if you go to machine learning, you can think of machine learning as a subset of AI, where what we do is we try to learn patterns from the data. We can think of deep learning, which can be thought of as a subset of machine learning, where we use neural network with many layers. So what differentiate machine learning with deep learning is we can think of deep learning as having deep layers or large number of layers. So we can categorize machine learning system as supervised, unsupervised, and reinforcement learning. Supervised means you have a label attached to the data, or we can say that we'll be knowing what we are trying to learn. And unsupervised means we won't be having any label attached to the data. And reinforcement can be thought of as learning from examples. So for all these categories, we can use artificial neural networks. We can use artificial neural networks for supervised learning, unsupervised learning, and reinforcement learning. So for a beginner, we can think of artificial neural network as something that helps to learn features automatically. In the last session, we have seen the concept of features. So coming to the learning, so we have already seen that learning requires a large. So I'll be putting this side based on supervised learning. So from that perspective, I can say that learning requires a large set of positive and negative examples. So each example is labeled by a human. Some examples are used to train the system, and that samples are known as training set. That set of examples is known as training set. Some other examples are used to test the system. So it is known as test set. So this figure summarizes the whole thing. We are using supervised learning. We have a training data with labels, both negative and positive examples. We will be giving it to the machine learning algorithm. The algorithm outputs a model. So for outputting the model, that thing is known as training. The machine learning algorithm learns from both negative and positive examples, which are labeled by the human. And we will be testing the model generated. We'll be testing whether the model accurately differentiate between the negative and positive examples. The model such generated can be used for prediction. So for that, we'll be giving new data or a new sample without the label, and the model predicts whether it is a negative or positive example. So take the case of the task where we need to differentiate between a dog and cat, image of a cat and a dog. So we'll be having a set of images of the cat and dog. We'll be giving it to the learning algorithm. The learning algorithm automatically learns the features from the examples. So it may be the shape or the color. And based on that, the algorithm generates a model. And if after that, if you give a new image that may be of a cat or a dog, it can predict whether it is a cat or a dog. So that all depends on many things. First one is on how many samples the system is learned. The next thing is how efficient or how good is our machine learning algorithm is. And based on that, we have a model, and the model will be able to differentiate between positive and negative samples. So another important thing from a learning perspective is that we need a big processing power. So I will be moving to the hardware perspective of this. So the learning requires, first thing what we need to do is we need to collect the data. For the case of differentiating between cats and dogs, we need to collect images of cats and dogs. And sometimes we need to process it. The processing is important because sometimes we collect the images of cats, but maybe it contains images of dogs. So we need to remove that. Some images may not be readable. So we need to remove that too. Sometimes the image, among the cat images, there may be an image of a horse. We need to remove that. Sometimes we need to convert the image to a specific size, or we need to remove some other objects. So all these things comes under processing. We may be giving the name pre-processing for that also. So loading and processing is the first step. Next step is we'll be using the machine learning algorithm for extracting the features or understanding the features. That is known as training. And this training step generates the model, and we need to deploy this model in some server, so that if you give a new image, then it will be easy for the model to predict whether it is a cat or a dog. So we have two components here from a hardware perspective. One is a CPU, central processing unit, and another one is GPU, graphic processing unit. This loading and pre-processing or processing is done by the CPU. The training, which is very computationally intensive, means that there are many things that happens during training. The system will be able to extract the features, understand which features are important. We need to take some, for that, we need to take large number of images, extract the features, and adjust the weight. That is what we have seen in the last class. So this thing is done by the GPU or graphic processing unit. And this process generates the model, and this model can be deployed. This can be put in a CPU because it is not that computationally intensive. Or if you have a model and if you want to get the prediction, that can be done by CPU. That's not a computationally intensive task. So the popular programming language for this is, from machine learning perspective, is Python. We all know that. There are different hardwares used for this. One is GPU, graphic processing unit. The name graphic processing unit means initially it was used for playing games, speeding up the graphic thing. So the name graphic processing unit. And now we have tensor processing unit, which is actively promoted by Google, where the TPU can run tensor operations very fast. We'll be seeing that what the concept of tensors. So what are the benefits of using the GPU or CPU? This image summarizes this. The GPU is designed to execute thousands of threads in parallel. You can think of it like thousands of processing in parallel. And GPU is used for highly parallel computations. Compared to the CPU, the GPU has got more transistors are used for data processing. You can think of it as more processing cores. So this figure shows, the left one shows the CPU. And you can see that the green portion, that is, it has got 4 cores. Cores is a processing element. The green color thing represents the core. And you have different types of memory to speed up the thing. But if you move to the GPU, it has also memory, but it doesn't have different layers of memory. Usually the memory in a CPU will be much bigger than some cases. Memory in CPU will be bigger than that of GPU. But if you see the processing cores, the green thing, the GPU has lot many cores. So lot many cores means lot more processing power. It can process data easily. So if the CPU has got 4 cores, I can say that GPU will be having 1,000 of cores. So that is the advantage of using a GPU or CPU for machine learning tasks. So this is the GPU computing architecture, or maybe I can call it an ecosystem. So I have here a layered architecture where the bottommost layer is the hardware, that is the GPU. Above that, we have libraries, which is written in usually C or C++. Some important ones are CUDNN for deep neural networks, QBLAS, QFFT. And part of these libraries are something called frameworks. We have most common frameworks are, one is TensorFlow, which is promoted by the Google, and PyTorch, which was promoted by Facebook. Now it is an independent free software project. So people can use either TensorFlow or PyTorch. Both these frameworks can be used using Python. And as the figure shows, you can see that both of these make use of the underlying libraries, CUDNN, QBLAS, QFFT, which is run in C++. So the thing is that you can write the code using Python, making use of TensorFlow, and which in turn can call these CUDNN, QBLAS, and QFFT to get the things done. And you can write the program in either C, C++, Fortran, Python. So if you are using C, you can C or C++, you can directly call these libraries, which is part of CUDA SDK. And on top of that, our application runs. You can think of it like it's having a layered architecture. So that comes to the question, what is CUDA? CUDA is a CUDA stands for Compute Unified Device Architecture. It is a proprietary parallel computing platform developed by NVIDIA in 2006. It includes a set of specialized libraries, highly optimized for machine learning tasks. It contains a large number of libraries. The important ones are CUDA Deep Neural Network Library, basic linear algebra operations library called QBLAS, and an SDK called the TensorRT, which is for optimizing models, specifically for inference. So it works on host and device model. So if you take a computer which we use for training and machine learning tasks, it will be having a CPU and a GPU. You can think of the CPU as the host and the GPU as the device. So what we'll be usually doing is we'll be moving the data from the host to device, the host memory to the device memory, and does the processing. That's what we usually do. Since 2017, NVIDIA has integrated Tensor cores into its GPU, which makes it easy for NVIDIA GPUs to do the specialized metrics processing, which we call it by the name tensors. We'll be coming to that. So I'll be using some slides to understand the concept of GPUs. We have already seen an image of GPU in the last session by Sunil sir. So I'll be explaining some very basic fundamental things to understand about GPUs. So most of the sessions and most of the time someone speaks about GPU, they'll be saying NVIDIA GPU. Don't think that NVIDIA is the only company that builds the GPU. There are companies like AMD that also builds the GPU, but the thing is that NVIDIA GPU is the most popular one. So that most language frameworks support NVIDIA GPU by default. So everyone use NVIDIA as a default GPU for programming. So this GPU has its own architecture by some code name. You can see that code name is a number. It has also got a name. It increases. The current one is 12. It has got a major revision number, minor revision number, and a patch number. So 10, 11, 12, these versions are known by the name Blackwell. Version 9 is known as Hopper. So if you take a GPU, you can see that you can see this name. It is based on Blackwell architecture. You can see the Hopper architecture. So what is the significance of this? By looking at the number or the architecture, you can understand the feature supported by that particular hardware. So if your architecture is, your major revision number is 5 or Maxwell, someone say that I have a GPU which is based on Maxwell architecture. So it may not be having all the features of the current GPUs. Most of the time it won't be able to, your program won't be able to run on that GPU also if your program uses some specialized features of some newer architectures. So if you are buying a new GPU or looking at understanding it, definitely look for the GPU architecture. So next we'll see the programming abstraction. So where basic we know what we need to know about how the GPU works. From programmer's perspective, GPU has got different streaming multiprocessors, and each streaming multiprocessors has got different CUDA cores that all are hardware things. From a programmer perspective, from a logical point of view, these streaming multiprocessors or cores can be divided into different grids. And grids are in turn divided into different blocks, and each block has got different threads. So you have a thread groups, shared memories, barrier synchronizations. These threads are organized hierarchically into blocks, or which in turn grouped into grids. Then there is a concept of shared memory. The memory shared by threads of the same block, and synchronization, where threads can coordinate their work and wait for each other. So the bare basic thing you should understand is there are different blocks and there are different threads. There are different ways of arranging these threads and blocks. So this shows the scalability feature provided by CUDA. So what the figure shows is, say if you are writing a multi-threaded CUDA program, say it has got 8 blocks. So if your GPU has got 2 streaming multiprocessors, it can be arranged like this. Say you have 8 blocks, then if you have 2 streaming multiprocessors, your CUDA will put first, say if it is 4 blocks, 8 blocks, first 4 blocks in first streaming multiprocessor, and second one is second streaming multiprocessor, if you have 2 streaming multiprocessor. If you have 4 streaming multiprocessor, then the CUDA will automatically, the C++ will automatically put 2 each in each of the streaming multiprocessors. So the programmer does not worry about this. So where to place the blocks, that are all our hardware things that will be taken care of by the compiler. So I have showed you a slide where the graphic processing unit will be having different blocks. So, and each block will be having different threads. That all what we need to understand. And the maximum number of threads that is allowed in a block is 1024. And it depends on the compute capability of the graphic processing unit. So for a GPU, we have different types of cores for different tasks. We have CUDA cores, tensor cores, and RT cores. We need to know about the CUDA cores and the tensor cores. CUDA cores are general purpose cores. They can do floating point integer operations and operations like that. But tensor cores are different from CUDA cores in that they are specialized for tensor operations. For now, you can think of tensors as n-dimensional array. So in the last class, we have seen that everything is represented as numbers, and the machine learning algorithm process these numbers to generate the model. So you have practically what you can think is you have large number of n-dimensional arrays or tensors. And in order to do the tensor processing or this matrix processing or n-dimensional array processing, you have tensor cores. And RT cores are graphic specialized things. They are used for ray tracing operations. That is not of concern to us. So what this CUDA cores does is it can do graphics rendering, physics simulation, and like that. And tensor cores are specific for tensor-based operations. Next, we will be seeing the different graphics card available. So if you want to buy one, you can buy in a desktop or a laptop. You can look for GeForce. GeForce is the brand name NVIDIA used for consumer graphics cards. You can see this graphics card in the laptop, or you can buy one for putting it in your desktop. They have got good CUDA compute performance. Good CUDA compute performance means they have a decent number of processing cores, decent enough for academic projects and all, maybe for your research. And the main thing is they are affordable. You can get it as low as some 5,000, 6,000 rupees. They are inbuilt in your laptop. When I search Amazon or Flipkart, I can see that I can buy one with CUDA cores with some 45,000 to 50,000 rupees. Then there is something called GeForce RTX Pro series, which will be having relatively more number of cores compared to RTX series. Then if you are much more serious, you can go for NVIDIA A series. These are for enterprise data centers. I have seen this A series in some academic labs, maybe some universities. Then NVIDIA H series for high-end AI supercomputing. Basically, it means that it has got more number of streaming multiprocessors, and in the end, which means that more number of CUDA cores. So if you can afford that, the easiest thing is you can use Google Colab. Most of you might be knowing Google Colab. Google Colab is a front-end service, software as a service provided by Google, which is based on the Jupyter Lab framework. You can think of it as a Python front-end. So where you can access the graphic processing unit, GPUs, for free. But it is limited. But if you subscribe to Google Colab, you can get the more popular graphics processing, or the ones with more computing power, like A series. So Google is not the only one provider which provides graphics GPUs. You can use Kaggle. You might be knowing the site Kaggle, which hosts data set and models. They have a free plan where you will be getting graphic processing unit, GPU based servers for training, but with a limited number of time. There are certain other cheap providers like Indian Ocean, where you can subscribe to their service and you can get A series and H series computers equipped with this graphic processing unit. So these are some of the popular GPUs. So NVIDIA releases GPUs very often. It's actually be difficult to keep track of the recent series. So I have put some common ones. The first one is RTX NVIDIA GeForce RTX 6000 series. So it is based on NVIDIA Atal Lovelace architecture. It has got 18,176 CUDA cores, 568 tensor cores, and 48 GB of memory. This memory means the virtual memory supported by the graphic processing unit. So if you are buying a graphic processing unit or you subscribe to some service that provides this, or using some GPU for your research purpose, two things you need to look at. First one is the number of CUDA cores or streaming multiprocessors, and second one is the amount of virtual memory it supports. Otherwise, you cannot put the data from the host to device. There will be a limitation on amount of data that can be held in the graphic processing unit memory. So if you look at A100, which is released in May 2020, it is based on Ampere architecture. It has got 6,912 CUDA cores with 432 tensor cores and 40 GB of memory. 40 GB is very decent for most of the tasks. So this is an overview of that. Recently, the NVIDIA has released something called DGX Spark. You might have seen that. We can see the figure Yan LeCun, which is holding. He has got Nobel Prize. He is inventor of this CNN. He's holding the DGX Spark. This image is released by NVIDIA. They are selling it as, they are marketing it as a desktop AI supercomputer designed for developers and research. You can see that this very small, the small form factor of it. It is having a desktop form factor. It is based on their latest architecture, Grace Blackwell. It has got 5th generation tensor cores, support AI models up to 200 billion parameters, 6,144 CUDA cores. So different manufacturers like ASUS has got this device. So ASUS has got ASUS Ascend GX10. I'm not sure whether it is available in India or not. It cost some, last time when I checked, it cost some 4,50,000 rupees. But with that, you will be getting a desktop form factor, a supercomputer. So everyone talks about NVIDIA. So what is so special about NVIDIA? So the first product for them was GeForce gaming graphics cards for personal computing gaming. First processor with the CUDA cores was released by them in 2006 called GeForce 8800. Then they released Tesla series in 2007, RTX series in 2008. In that, they have introduced the tensor cores. It is specialized for tensor processing. And recently, they became the first company in the world to hit $5 trillion market cap just by selling the graphics cards. So that says the interest in this. So if you look at the share price, it was something $50 into 2020. In 2024, it went to 1,064. So that is a huge rise in interest in NVIDIA. So we move to some programming perspective. So assuming you have a CUDA-based laptop or a desktop, you need not worry about this thing if you are using Google Colab. So I am assuming that you have some desktop or a laptop with CUDA-based graphics card, NVIDIA graphics card. First thing is, what you need to do is you need to install the CUDA driver. Second thing is you need to install software development kit, SDK. It is needed for writing the programs. So in order to install the SDK, what you can do is you can download CUDA toolkit first. CUDA toolkit means, as the name suggests, it is a set of tools along with the SDK for programming. So if you are writing the program in C, it will be having a compiler called NVCC. If you have written the program in Linux, you might be knowing C compiler. Here it is known as NVCC. So basically, you can write the program in C++ or Python. If you want to write some specialized program, you can write a program in C++ or C. Or you can write, if you don't want that much optimization, you can write the code in Python using the libraries which we have already seen, TensorFlow or PyTorch. And it will automatically convert the code so that it can be run using the libraries, CPP libraries. So we will see some basics of that. So I am running this in a laptop with a graphics card. So if you have this toolkit installed means you will be having the software development kit installed or the CUDA driver installed. We can check whether the driver is working by typing the command NVIDIA -SMI, NVIDIA -SMI. So it outputs the driver version, software driver version, the CUDA version, CUDA software version, that is 13. It's the latest one. It also lists out the graphics card. In my laptop, I'm having GeForce RTX 4050. It's a decent graphics card. So if you look at so I forgot to switch the screen. So you can write NVIDIA -SMI, and which will print the driver version, CUDA version, and the graphics card I am using. Here it shows NVIDIA GeForce RTX 4050. The amount of memory available, the amount of memory taken, the processes running that make use of this is graphics card. CPU memory usage, currently it is only 89 MB. So if you see the RTX 4050 graphics card, it has got 2560 cores. Here 2560 cores means 2560 CUDA cores. And it has got 6 GB of virtual memory, graphics memory. That is decent for most of the tasks. And you can see the SM count, streaming multiprocessor count. It has got 18 streaming multiprocessors, clock frequency and all. So it is based on Atal Lovelace architecture. So generation is GeForce 40. It is a consumer grade one. So next we will be seeing how to write a program using C++. And after that, we will be moving to write the same thing in using Python. So we'll start with a vector addition example. So what we have is, you have two arrays. One is A, we just got the values ones. The size of A is 1000. You have 1000 vector of an array of size 1000. And another array, which is also of size 1000. Just got the value 1, integer 1. And what I'll be doing is, I'll be taking the sum of A and B and storing it in C, where I will be getting the output 2, which is the sum of both each of the element of A and B. So if you are writing this program using C, the normal way is you will be using a loop to loop through the elements, both A and B, and summing it up and storing the result in C. That is what we are doing. But in the case of CUDA logic or parallel computing logic, what we'll be doing is, we'll be telling the threads to take the element at some index and do the computation. The computation here is the sum of A and B. So I can say that the first thread will be doing C0 equal to A0 plus B0, or what the first thread does is taking the value of zeroth index, summing it with the value of zeroth index of B, and storing it in the zeroth index of C. So first thread does C0 equal to A0 plus B0. The second thread does C1 equal to A1 plus B1. Third thread does C2 equal to A2 plus B2. Likewise, the 1000th thread does C9999 equal to A999 plus B99. So we can see that the index number starts with 0. So for that, we won't be writing any loop. What we will be doing is we will be specifying the number of blocks and threads needed. So in one of the last slides, I have already explained that maximum 1024 threads are possible. So in a block, so you can use a single block, or you can use n number of blocks. That depends. That is a programmer's prerogative. So this figure shows I have 4 blocks, and what each block does is each block takes 250 threads, which means that block 0 will take 0 to 249, that is 250 threads. Block 1 takes 250 threads. Block 2 takes 250 threads. Block 3 takes 250 threads. And this sums up to 1000 threads, and each thread does this. So the code here is, I can write int I equal to inside a function. So I have something like underscore underscore block underscore void matrix art plot. So if you have written some C programming, you might be knowing this. You are passing the pointer address of A, address of B, address of C, and total number of elements. Then inside that you will be calculating. Inside that you will be calculating the thread ID, the ID which each thread will be doing, and you will be telling that you need to do, each thread should do Ci equal to AI plus BI. Here you can see that you won't be having any loops. Instead of that, you will be adjusting the value of the index for each thread to do. Each thread will execute it separately, and the value of I will be different for each of the thread. So the block 0 thread 0 will be having the value of I as 0. So it will be having C of 0 equal to A of 0 plus B of 0, likewise. So this function, the thing that does this addition, is known as kernel. So the standard name for is kernel. So before that, I have given the code that specifies the number of blocks and the number of threads per block. And I am saying that I need to instantiate or call the kernel matrix add with this number of blocks and this number of threads per block. Here you can assume that it is 4 blocks and 250 threads per block with the matrix or vector A, B, C, and the total number of elements. So this is how you do this. I can show you the full code that does this. How the screen is visible.
Yes, sir.
So if you are writing a CUDA program using C, for normal C program, the extension is C. For CUDA, the extension is CU. CU stands for CUDA. So this is my CUDA code that does this vector addition which we have seen. So again, here I have an array of size 20,000, and I'll be allocating the memory. Here I have used the value of A as initialized the vector A with 1 and vector B with 2. In the slide I had given both 1. So the program I have given the value of 1 to A's and 2 to the vector B. And there are some memory allocation things. I am not going into that. So this is the kernel that does the trick. Calculating the index and telling the thread to do C of I equal to A of I plus B of I. So the thing you need to understand that each thread will be having different value of I. The same thing happens when you will be, if you are writing, if you know the concept of threads in CPU also. So the kernel, that is the kernel. The invocation of that can be seen here. Invoke the kernel matrix chart with the blocks per grid and threads per block. So this will call this one. So next we will see how to run this. So the compiler we'll be using is, I have already said that is NVCC. You can write, if you are familiar with writing C program in Linux, and it will be easy. You can write NVCC. The program name, the name I have given is vector.r.cu. So this will generate a dot out, like what we get if you use GCC. Then you can write a dot out. So in the output, I am not outputting all the results, just printing some. So you can see that it is taking some time. It's actually 20,000 into 20,000. It's a big one. So it will take some time to print the result. So this is how you do the programming and the running the code. So if for a beginner, this might be some bit scary. So you need to write so many lines of code to do just a matrix or a vector addition. So if you connect it with machine learning, you will be having thousands of operations like this. So which means that you need to write lakhs of lines of code. So that is not the case. And that is why we are using the language Python and the library either TensorFlow or PyTorch. So I'll be showing the equivalent code in Python. So it is self-explanatory. And we have 1, 2, 3, 4, 5. That's all. 5 lines of code. So I will show you running this. So what we have done is I have used TensorFlow library. I have imported it as CF. Then I have defined the size as 20,000. In this program, I have used the size of 20,000, vector of size 20,000. In the earlier one, I have used 20,000 into 20,000 matrix. Here it is 20,000 only, vector of size 20,000, is of size 20,000. And I have used a method called fill to initialize that matrix or that vector with the value 1 and initialize this vector with value 1. So both A and B is having the value 1, and I will be calculating C equal to A plus B. So when I run this using TensorFlow in a GPU, your interpreter will automatically convert this code such that each thread will calculate the index and calculate C of I equal to A of I plus B of I. Thus, that thing will be taken care by the interpreter, or that will be done by the framework, so that you can write this code with much smaller number of lines. So if you are writing a program, or if you are doing machine learning, you just need to study Python. You need not study the writing program using C. That all things are handled by the Python and its framework. So we are moving to that. So there are different libraries for doing machine learning using Python. One popular one is PyTorch. It was developed by Facebook Fair Lab. It is the same lab which the person Jan LeCun was head recently resigned from this lab, and they developed this PyTorch. First version was released in 2016. It is actually based on another language called Lua. PyTorch was initially a Python port of the Lua code. Now it is maintained by a non-profit foundation, Linux Foundation and PyTorch Foundation. It's a non-profit. Then we have TensorFlow, which was developed by Google Brain Team, released 1 year or sometime before PyTorch in 2015. So the thing is, if I am comparing TensorFlow and PyTorch, if you have GPU, TensorFlow will try to run the code in GPU itself. I can say that also. Then the Keras was another independent library which was written on top Python, which made it easy for programmers to write machine learning code much easily than using TensorFlow. It was developed by a person called Francois Cholet in 2015. You can think of it as high-level API of TensorFlow, something which is written over the TensorFlow to make things much more easier. Now, with the new version of TensorFlow 2, this Keras is integrated into TensorFlow. So, if you want to use Keras, you can just install TensorFlow itself. But this Keras supports TensorFlow, PyTorch, and JAX. JAX is a recent framework. So there are two choices. If you are writing the ML program, you can either use PyTorch or you can use TensorFlow. So most of the people here in India use TensorFlow. I have seen that people outside use PyTorch. It is said that PyTorch is more Pythonic in the sense that you are creating some object and you can calling a method on top of that. That is how you write code in Python object-oriented way. So that way is most that way can be done using more easily in PyTorch compared to TensorFlow. So if you are good at programming using Python object-oriented way, then PyTorch might be a good start. The functions are more or less similar, maybe some name change. If time permits, we will see both TensorFlow and PyTorch. But the focus of this session is TensorFlow. So before going to that, we need to understand the concept of scalars, vectors, and tensors. So scalar means a single numerical value. Vector means ordered finite list of elements, the number of elements. Tensors can be thought of as multi-dimensional array with the same type. Tensor should be of the same type. So for now, you can think of only the change of the name, or you can easily think of as it as a multi-dimensional array of the same type. So if you have a matrix, you can think of it like matrix is a tensor. So you can think of it like tensor as generalization of all these. A vector is also a tensor. Scalar is also a tensor. Everything can be abstracted to a tensor. The tensor can be 0-dimensional, 1-dimensional, 2-dimensional, or n-dimensional. We will see that. So before moving to that, we need to understand the concept or the vocabulary of that. So there are three things you should understand. First one is shape. Shape means number of elements of each axis. So if you take a color image, in the last class, by Sunil sir, we have seen that. It is 3-dimensional. 3-dimensional in the sense that it has got height, width, and 3 channels, RGB, red, green, blue, for the color channels. And if you look at the shape, it has got some height, some width, and some number of channels. So in the case of an image, it has got 3 axes, height, width, and the channel. Number of elements of each axis is the shape. Rank means number of axes or dimension. In the case of an image, it is of 3 dimension, height, width, and the number of channel. Size means total number of elements in the tensor or the object we are considering. Total number of elements. Number of elements will be having. So this is a basic vocabulary we need to understand for understanding tensors. So we'll be moving to the generalization of the tensor concept. You can think of matrix as a computer programmer. We usually deal with the matrices. A matrix is a 2D array of scalars, or you can think of it's a collection of vectors. Each row is a vector. So you can say that it is a collection of vectors. And the elements of each of these vectors are scalars. So if you have a 2x2 matrix, each element is a scalar, some integer value or a floating point value. And if you consider the tensor, this matrix, which is of 2-dimensional array, is a tensor. Or I can say that a tensor generalizes scalars, vectors, and matrices to n dimension. So if you have something in 0-dimensional one, which is actually a scalar. If you have a 1-dimensional one, which is actually a vector. If you have a 2-dimensional one, which you can think of it as a matrix. If you have 3-dimensional or n-dimensional, you can say that they are all tensors. Or you can say that tensor is a general name used for this. So now we are going to tensor representation. So both this TensorFlow, PyTorch, and if you have used NumPy, they use n-dimensional arrays. In the case of NumPy will be giving, we are not using the name n-dimensional arrays. We are using the name n-dimensional arrays, not tensors. But all of these supports the concept of tensors, or maybe I can say that n-dimensional arrays to perform operations on GPUs. So So I have a typo here. The scalar one is here, it is should be 0. Rank is 0. So rank is 0 means a scalar means say some integer value 5. So it is of shape like this. So if you have a vector, it is of shape 1, rank 1. For example, we can say that it's a vector with 3 elements. We have 3 elements. The shape will be printed as 3 comma, which you need to understand that it represents a vector with the 3 elements. These 3 elements are 1, 2, and 3. So here we have a matrix. Matrix with this matrix is having 2 rows and 2 columns. So it will be shape is 2, 2. So if you take an image, it has what height, width, and channels. 3-dimensional, rank 3. I'm not printing the shape. So if you consider the video, you can, in terms of an image, video can be thought of as something having a number of frames. Video is made up of number of images. So video is of rank 4, which is having frames, n number of frames. Then the image feature, height, width, and channels. So this is how you represent tensors. Tensors are multi-dimensional arrays with a uniform type, single type called a D type. We are coming to that. The major types are TF.432, TF.32-bit float, 32-bit integer, even 64-bit integer is possible, unsigned integer, 8-bit. All tensors are immutable. Immutable means you cannot change the value. So if you want to change the values, you need to use the concept of variables. So this TensorFlow, if GPU exists, put the tensors on the GPU. You can put it on CPU also. Functions for that. So you can easily convert to these tensors to number arrays for processing. Operations are vectorized, which you will see later. We will start with some examples. So in the session, I'll be using Google Colab. So Google Colab is, as I told you earlier, Google Colab is a free service provided by Google. You can also subscribe to that. So you'll be getting a screen like this. I'll be increasing the size. So this is specialized for machine learning tasks. So you need not worry about installing the libraries and all. TensorFlow is installed by default. So if you want to use the TensorFlow, you can import it right away. You can type import TensorFlow as TF and run. So you can see that it is connecting to the kernel. Here kernel means Python. So it will take some time. So connected. It will be running. So it will take some time to load the module since we are using the Google server. Sometimes it may be busy. So if the import is okay, we'll be seeing a tick mark. So in the right side, you can see the statistics of our hardware. You can see that I have a system RAM of close to 13 GB RAM, disk space of hard disk of 100 GB. So in that I have an option here I will be getting a drop down box. I have an option to change the runtime type. By default, CPU will be selected. So if you want to use GPU, you can select the GPU you want. Actually, I have subscribed to the Google Colab, so I have some more GPUs than provided in the free tier. You can see that you have 100 GPU, which is a professional grade one. You can get that. You have L4 GPU, T4 GPU. You have also some TPUs also available in the subscription. And this Google Colab runs Python 3. So that's so you can the place where we write the code is called cell. So we'll be creating some tensors. So we have imported the TensorFlow TF. So we have 5 more minutes. So I am a bit slow on time. We will continue. We'll stop at sharp 9:30 and continue tomorrow also. So I am creating a variable scalar equal to TF which we have imported. TF dot, that's a method called constant. So if I am creating a scalar, I can write TF dot constant 5. The same thing which we used in our example. So it is stored in the variable scalar. I can print the value of scalar. So I can see that scalar is of type, it is not a scalar, it is actually a tensor with the value 5, shape equal to a constant scalar. D type, by default D type is into 32-bit integer. I can also print out some properties. I can type scalar dot shape. This will print the shape, which is already printed if I print the scalar. I can print the number of dimension, called the property ND. Since it is a scalar, the number of dimension is 0. So next we will create a vector. So you need to put square bracket. The same example I am using. The values 1, 2, 3. A vector with 3 elements. So I have created a vector. I have stored in the variable var, not to confuse. So I'm running this. So variable var is a vector. Shape 3 comma means you need to understand that it is a vector. It is again also of type int32. Now we'll try to create a matrix, 2x2 matrix. So you need to understand these things. Put everything in square bracket. Put every row in square bracket again. So I am creating a 2x2 matrix. So first one is 1, 2. First row, 2 elements, comma. Then I move to the second row. That is 3, 4. So this way you can easily create a 2x2 matrix or a tensor. So it is a tensor with values 1, 2, 3, 4. Shape is 2, 2, which means that it's 2x2 matrix. Again, D type is 32. So likewise, you can create 3-dimension, 4-dimension, likewise. So it's almost 10:30. We can stop it here and continue tomorrow. If you have any questions till now, you can ask. Otherwise, we can stop.
Participants, if you have any queries, please feel free to ask now.
No questions, I think.
I think no questions from the participant side, so that we can conclude the session. Thank you, Justin sir, for the informative and practical session. Your clarity and hands-on approach have greatly enriched our understanding of AI programming. Thank you so much, sir. So for the participants, the WhatsApp group link has already been shared in the approval email. Many participants still haven't joined, so please make sure to join the WhatsApp group at the earliest. The feedback link for today's session has been shared in the Google Meet and in the WhatsApp. Kindly fill it without fail. And the tomorrow session will begin at 6 p.m. Thank you all for your active participation today. Looking forward to seeing you tomorrow. Thank you so much, all dear participants. Justin sir, one question from the participant side.
I have seen that. The question is, what need to prioritize, VRAM or core? So the obvious thing is you need to prioritize the cores. Since you can, if the RAM is limited, we can move some part of the data to GPU and do the processing and move it back. But there should be some balance. If you have a large number of cores but very less number of VRAM, then there won't be any use in having that much large number of cores. But if you have very large number of VRAM, large amount of VRAM, but very less number of cores, it's actually like CPU. It won't make much difference. But these NVIDIA people have put a balanced approach on that. So if you can spend much more money, you will be getting the one with more number of cores and more number of VRAM. The best thing is you can use Google Colab.
Thank you, sir. Thank you for the answer.
So I think there are no more questions from the participant side. So we can wind up the session today. Thank you. Thank you so much, dear participants, for your active participation.
Thank you all.